Okay, so for today, we're going to look at today's topic will be the second hand rule. Okay, so I'm going to say a quote unquote different hand rule. And I say quote unquote because really it's just an extension of the first hand rule. Okay, so don't get too flustered with remembering all the second hand rule, all the first hand rule. Okay, they kind of lead to each other. So yes, you're going to apply them a bit differently, but the idea is still the same here. And the first hand rule, like I said, kind of leads to the second hand rule. So if you're looking on page 6 of your notes, you'll see where the first hand rule notes section ended. There was something that said connection to the second hand rule. So we're going to start there. Okay, so that's what this picture is. I've just printed it out a bit bigger so you can actually see what I'm doing. So we have the direction of current, for example, on this one. Okay, so remember in our first hand rule, it was for current or electron flow or whatever, moving charge in a straight line, right, through a straight conductor. Great, awesome. Okay, so when it was going like this, easy peasy, we can figure out the magnetic field. Now, that doesn't actually change if the wire, if the wire and the charge moving through it is no longer a straight line. We can still say, okay, thumb points where the charge is moving, magnetic field is still the fingers. So for example, this one, at that point where they've grabbed it, right, you can see, okay, the magnetic field at that point, since they did current, right, since current is going this way, so it's a positive, so we'd use our right hand rule. Okay, we can see, it's here, it's kind of coming out of the page towards us, right? Kind of like that. They've drawn on a bit of an angle, but you could even think of it as dots, essentially. It is on a bit of an angle, but more or less dots here, X is here, right? Everywhere as I go, what if I go up here? Okay, what if I grab it up here? Well, where's the magnetic field? Right? If I'm looking up here and current is now going this way, as it's just making its way around this looped conductor, right? Same thing, still dots for the magnetic field. They're still going to be coming out of the page here, right? Same thing here. So kind of everywhere in here, I have dots. What about out there? Well, everywhere outside of the loop, right? I'm going to have X's. Okay, cool, great. So think about what that means for a sec. We have magnetic field lines that are always, whoops, I should have been doing these purple. Sorry, there are a few times I've been inconsistent with my color coding. Please don't think you're misunderstanding or anything if you're saying, hang on, that was supposed to be purple. I'm trying to keep it color coded, but it's not always going to be the case. Okay, whoops, and then I just made current purple, which current was supposed to be the blue thing. Sorry, I'll try and be consistent. Just don't panic if you're thinking, hey, that's not supposed to be that color. Okay, so notice here, everywhere here, we have the magnetic field coming out of the page, right? And then everywhere around it, it's going into the page. Is this maybe starting to look like something? We have a magnetic field that in here, it's coming out. On the outside, it's going in, okay, and then looping back around and coming out. Might start to look like something. We'll get there today. Okay, same thing here, same idea. If I go along and I grab this wire at a bunch of points, okay, so blue, I'll try to be consistent. Blue is current, right? So at any point along here where current is flowing, okay, you can grasp the wire, right hand, because it's positive current. And notice no matter where you are, your fingers are going into the page outside, right? Into the page outside. So the magnetic field is into the page outside of this loop. Okay, and what about inside the loop? Well, right? If I grab it over here, where are my fingers pointing? They're coming at you. So anywhere in the loop, we have dots, right? Okay, so again, same idea here. The magnetic field is coming out of the page at you at some point. It's looping around, going away, right? And then presumably coming back. Okay, this one starts to really give us an image of where we're going with this. Okay, now look at this. So same idea, essentially the same picture, just with given a bit of a push in the direction of where we're going to be going, right? They've actually labeled some poles here. So again, take current, right? Go around, grab it anywhere, okay? Now, careful, these field lines are all coming from inside the loop, right? But for example, this little part here, right? If you're grabbing here, yep, sure enough, the field lines, first they'll be coming up kind of that way towards the top of the page, and then they'll go down, and then they'll loop back until they're coming back at you, back at dots, if you were to look at it from up here, right? So if your eye was up here, you'd be seeing these as dots. Let's think for a sec about a bar magnet. I got a real one here, okay, and then I can take it away and we can think about what's actually happening. But remember, the magnetic field lines, what do? Where do they go? They leave north, right, and they enter south. Whoops, leave north, enter south. Should be going that way. Leave north, enter south. Okay, and again, there's ones that go like this, but always leaving north, always entering the south pole, right? And then I would think about, okay, what's happening inside the magnet? Well, they enter south, and then what's next? Once you enter south, you got to leave north. So how do you do that? Well, you have to travel through the magnet, right? And then those field lines actually meet up, same field lines, right? They leave north, go, enter south, right? Even these ones are kind of the same thing as happening there. They are entering south, and then they're going to leave north, right? Entering south, and then they're going to leave north. So what direction is the vector within the actual magnet? It's pointed this way, right? It's pointed this way along to north, okay? So the field lines within the magnet only, they go from south to north, right? Because they just entered south and now they're headed to north to exit, right? So notice now, let's connect this to our field lines here. Which way are they going? They're going this way. Okay, so is this then kind of look somewhat familiar to you, right? Take a look at that. Imagine these, what are they going to do, right? You can see they're starting to do it. If this picture were a bit zoomed out, we actually might see them do it. In fact, this one did it, right? These are going to loop back, enter south, right? These are going to loop back and enter south. Should really be starting to look familiar now. Loop back, enter south. Okay, so see how, and then what do they do in the middle? Just like they said, right? They have to, if they're entering south, they've got to leave through north again. So we're going to now take a hand rule that explains this, but when you have a curved conductor, a circular conductor, okay, as we know, moving charge induces magnetic field. When we have a circular motion for the charge, it can actually kind of give us this magnetic field in a particular direction, where you can actually start to think about it in terms of a north and a south end because of those interactions all the way along. So we'll use the second hand rule to now kind of think about it, but I just want to be clear, it's not a different phenomenon than the first hand rule. It's just because we're changing the motion of the charge, we can kind of change the way the electric field is expressed so that it's expressed in a way where it actually kind of has these magnetic field lines that resemble those of a bar magnet. Okay, so is there an easier way when we have a circular conductor than using the first hand rule a whole bunch of times and kind of figuring out all the interactions? Yes, there is. Okay, I just wanted to show you that it's not really a different idea. It comes from the same place, but there is a better kind of rule to use to help you wrap your head around it. So for the second hand rule, this is when we have a circular current as opposed to the first rule when we had a straight current or a straight moving charge. Okay, we use the second hand rule for, again, circular currents or coils, okay, or solenoids. We'll get to those in a sec. So now your fingers, okay, so before your fingers were the magnetic field, now your fingers are actually the current or the electron flow, again, just the thing that's moving. Nothing changes here though, it's still left hand rule for negative charges, okay, left hand rule for negatives, and the right hand rule for positives. I just realized I usually use red for negative. So nothing changes there. That's never going to change, any of our hand rules. Okay, but now our thumb points towards the north pole of our magnet. So thumb points north. Okay, you got to kind of imagine that your thumb is inside the coil. That kind of helps you think about it because that is where we're talking about the magnet. Like I just showed you on that diagram, right? It's within the magnet that we kind of have those field lines adding up. So again, if you look at this one, right, you can kind of see that. What does the magnetic field look like? Well, in all magnets, right, it enters south and leaves north, right? So along this way. So your thumb is still pointing along the magnetic field, right? It's pointing within the magnet, right? Within the coil of the wire, which is our electromagnet. Okay, it's pointing in the direction of the magnetic field. And again, if you're not convinced, use your first hand rule. Look at all the little coils here and see if you can kind of see how they add up into sort of a more straight magnetic field. So a way to think about this is first hand rule is for circly magnetic fields and straight currents. This one is more for circular currents and within the coil at least a more straight magnetic field, right? There's a clear south and a clear north. Okay, so hand rules are great, but we should, before we just kind of trust them, we should make sure they actually can explain something physically that we can observe. Okay, so to show you that, let's start with what we have here, an electromagnet. Might not look like one now, and I guess technically it's not because it's not hooked up to current. Okay, but we essentially have here a steel nail with a bunch of wire wrapped around it. Okay, so a circular conductor. Okay, so when current flows through there, it'll be going in a circle. Now, the steel magnet is not necessary 100%, but what it does do is A, kind of strengthen the field, B, just give you something to wrap the wire around. So I want to be clear, without the steel nail, this could still act as a magnet. All you require is a circular current. But the steel magnet also makes it a bit stronger because steel contains iron, which is, of course, ferromagnetic, right? And so when we have the magnetic field induced by the current going around in a circular path, okay, the domains in the steel magnet will also get aligned along that magnetic field, that induced magnetic field, okay? So what that'll do is cause the steel to be acting as a permanent magnet as well. It is almost like a bar magnet, okay? But again, to be clear, the nail does not need to be there. It just gives you something to wrap wire around, makes the effect a little bit stronger. Okay, so how am I going to hook this up? Well, I've got a battery here. Okay, this time I've labeled the negative and the positive terminals. I'm not going to hook it up just yet, but I'll show you what I'm going to do. Okay, I'm not going to hook it up just because I know it's going to be hot. It gets hot pretty quick. Okay, I'm going to attach this to the negative terminal there. Okay, so what's going to flow this way? Well, what leaves the negative terminal? Electrons, right? So they are going to flow. They're going to flow through, whoops, they're going to flow through this wire, right? Through this wire, and then they're going to enter the coil. Okay, they're going to travel through that. They are going to, I don't know if you can see, they're going to come up kind of over and then down. So when they're in front of the nail this way, they're going to be going down, right? And then when they're behind, they're going to be going up. So down in front and then up behind and then down in front until they get here, and then they go through there back to what I'm going to hook up to the positive terminal. Okay, so looking at this, okay, can we apply our hand rule to make a prediction and see if it actually checks out, see if it actually works out the way we would expect it to? So electron flow is what I'm thinking about. You can use current if you want and check my work. I'm going to think about it as electron flow. So when I hook that up, electrons are going to be going this way. Now, as I said, right, they're going to be coming up, over. Can you see that? They're going to be coming up, over, and down in the front. So they're going to be down in the front, left hand down in the front, right? Each time they wire around, they're going to be going down there and then up back. So where is the north pole of this electromagnet going to be? Well, it looks like it's going to be the head, okay? The head of the nail, not the stabby part, because I am pointing, if my thumb points north. So according to the left hand rule, this should end up being the north pole of the magnet when we hook it up. Let's just see. Let's hook it up and see what happens. So negative attached. I need to complete the circuit. Okay, reminder, I have this hanging here. This is going to be my test magnet. I'm going to see if it follows the rule, right? So if this is going to be the north pole like the left hand rule, or the second hand rule says it should be, okay, then it should attract this thing's south pole and repel this thing's north pole. So reminder on these bar magnets, red is north, blue is south. Okay, so let's just see. Let's hook it up, see what happens. Again, the head should be the north pole as we kind of predicted with our second hand rule. Oh, whoops. Okay, let's see. So what does it do? Oh, look at that. It's attracting the south pole. What does it do to the north pole? Sure enough, the head, okay, is the north pole and it is behaving as such. What about this side? So the stabby side. Look at that. Now it's attracting the north, so the stabby side is the south, just like we predicted, and it is repelling the south. So seems like the second hand rule works. We've now used it to predict something actually physical. Okay, checks out. What if I reverse the current? Okay, so what if I cause it to flow the other way? Well, let's think about that in terms of our left-hand rule. So instead, I'm going to hook the black one. Before I had the black one hooked up to negative, I'm going to hook the black one up to positive and the red one up to negative. So where are electrons going to come from now? Well, now they're going to flow through this, right? So they're going to flow through this, and now they're going to start over here on the stabby end of the nail, okay? So what are they going to do? They're going to go up and over. So now in the back, they're going down, right? Now in the back, do you see that? They're going down, and then they're going to come up, and then they're going to be going down. So if I use my left hand rule, now they're going down in the back, right? So now they're going down in the back because of I'm changing the fact that the electrons used to be going this way. Now I'm going to make them go this way, right? So now when they go through the coil, they are going down in the back. And if I kind of grab it that way, right, where does my thumb point? It now points over here. So we're saying if I flow electrons in the other direction, now the pointy part will be the North Pole, as opposed to last time when the head of the nail was the North Pole. So now my thumb should point toward north. So since the electrons are going to be flowing that way, this pointy part should be the North Pole. This head should be the South Pole. So let's switch it around, okay, switch our wires around and see if we get the opposite reaction from our test magnet here. So this time black is going on positive and red is going to go on negative. So electrons are flowing the other direction. Again, you could think of it with current if you like. You just flip your hand rule. Use your right hand instead of your left hand. Okay. Whoopsie, did it again. Okay, there we go. So now, let's see. Now, what does the pointy part do? Aha, now the pointy part attracts south, right? What does it do to north? Repels north, attracts south, okay? Flip it around. Our head that used to be the north, when we had the other configuration that used to attract south, what does it do? It repels south. What about north? Attracts it. Cool, okay. So I'm gonna turn the current off. Ooh, hot. Okay, there we go. So is the magnetic field going to be as strong now that it's not being caused by, now that the current's not flowing? No, in fact, if there were no nail there, there would now be no magnetic field here at all. Okay, the thing is, this has been used so many times as an electromagnet. In fact, even just that, using it a little bit, will cause the domains to align, right? A little bit in this ferromagnetic material. So truthfully, this thing has kind of become somewhat permanently magnetized, right? So even with no current, it actually does attract a little bit, okay? However, if that steel nail weren't in the center, as soon as the current's off, there's no magnetic field anymore, right? Moving charge induces a magnetic field, not just charges sitting in a wire. The reason it kind of retains some of it, and you can even tell, look how much weaker that is, right? But that's because this has been used so many times. The induced magnetic field, as we saw yesterday, has caused the domains to align, and so this has become somewhat of a permanent magnet. That is actually how we can make permanent magnets. That's the method of magnetizing materials.
Kind of visualization here. You can see, wish you could slow it down a bit, right? But notice the electrons. Use your hand rule if you'd like. Okay, see if they're showing current or electron flow, right? You can kind of tell they're going up. So try the left hand rule and see if that looks right. Try the right hand rule and see if that looks right. And then tell me if these are electrons or current. Okay, so they're kind of going up. So you might, if you're using your left hand rule, then you will notice that your thumb is pointing correctly, right? It is pointing to north, as these all are, okay? We can also, if I change it to alternating current, which essentially means it flips so that they go back and forth. This is, right? Notice the magnetic field also flips. North, south, south, north, north, south, south, north. Okay, because the direction of the electron flow is changing. So you'd be, if you're doing it with your hand, you'd kind of be flipping back and forth between pointing to the left, pointing to the right. Oh, there we go. I can slow it down. Okay. All right, so look there. Now it's a little bit easier to try out your hand rules, right? I can even reverse the voltage, which essentially would mean changing how you're hooking it up to the battery like we did with ours, right? Again, try your hand rule, okay, but notice now your thumb would be pointing this way, and so does the magnetic field.
Okay, so now that we've kind of confirmed that the second hand rule does indeed work, okay, with a real physical application, let's go through kind of the examples that are on page 6 and 7 in the notes. We're just going to kind of work through them. Sorry, page 6, 7, 8 in the notes. We'll work through them and just kind of do them. I'm going to do them on here so that you can actually see my hand as we go, because it's not much help for me to just talk about it. Okay. All right. So looking at this thing here, the trickiest part for me of the second hand rule is figuring out where are the electrons flowing, where is the current going. Once you kind of got that, and it's not that it's super hard or anything, it's just it can be kind of a bit of a mind bender to wrap your head around it, or wrap your fingers around it, I guess I should say. Okay, so when we take our they're talking about electron flow, so which hand? left hand. Okay, so we're going to take our left hand and think about if I'm an electron, what am I going to do? So the fingers are going to, they're going to curl around. Okay, once you kind of got what they're doing on one side, it gets a little bit easier. So I think, okay, so they're going to go up, and then on that far side, they're going to be going down, right? Because they're going to come back. And then on this close side, the side of this picture, I guess, that's closer to us, they're going to be going up, right? So they go up here, they go down there. So over here, my fingers, over there, my fingers should be going down. Over here, my fingers should be going up. Sure enough, that does seem to be how it works. And our thumb points towards north, right? Not only does it point towards north, it points, if our thumb is inside the magnet, it's pointing in the direction of the magnetic field, right? So within the magnet, if it's going to leave north, it has to go that way, right? Go back around. So within the magnet, it goes that way, goes back around, okay? Same thing like that, right? That's what the magnetic field is doing. So our thumb always points to north. I can hear you kind of thinking, what if I used current? Would it still work? Yes, it totally would still work, okay? But we would have to change our hand rule. We would now use our right hand, okay? Still a second hand rule, but now our right hand. So what would I do if I'm a positive charge? So looking at the picture, I would go, okay, first behind, and then I would wrap so that, okay. So now when I'm in front, if I'm current, I'm going down in the front, right? But in the back, I'm going up, right? Down and then up. And it's kind of hard to do, but notice your thumb still points towards north. So if you're electron flow, you're doing this. But if you're current, you're doing this. So that either way, you end up pointing to north with your thumbs. Okay. So in the second hand rule, we have curved current or electron flow and a straight magnetic field within the coil. At least the magnetic field is fairly straight, right? Notice within the coil, it's all pretty straight that way. So for the first and second hand rules, you can kind of think of it as the curly thing or the curved thing is going to be your fingers, right? The straight thing is going to be your thumbs. That's always true. Okay, so if you have curly current, make those your fingers, and thumbs point north, right, in the direction of the straight magnetic field. Back to our first hand rule for a sec. If we had a current that was moving straight, right, well, then our curly thing is our magnetic field, and those are our fingers. So fingers are always the curly thing, thumbs are always the straight thing. Now this example is on page 7 of the notes, so just the next page as you flip. Okay, the question asks, if you notice on your notes there, it says, should you use your right or left hand? I mean, as we said, right, it doesn't matter as long as you're careful about which way it will flow. However, they have kind of set us up. They've given us a bit of an assist here, an alley-oop. They've already showed us this direction. But what are they showing with those arrows? Are they showing current or electron flow? Well, ask yourself, which way would a negative electron go and which way would a positive and pseudo-imaginary current go, right? Not that it's imaginary, but it's not actually flowing. Positive charges aren't actually flowing, so I guess it kind of is. Okay, well, these are going, notice they're going towards the negative terminal of the battery and they're leaving the positive terminal. So what would leave a positive terminal? What would want to get away from that? Positive charges, right? So this must be current. This is I, this is current. Okay, those arrows are showing current. So we don't have to. We could just go the other way and use our left hand rule, but since they set us up, let's go ahead and use our right hand rule. Okay, our right hand rule for the second hand rule. If you are a positive charge, what are you doing? Notice, okay, you're going down and then you are coming up. Okay, going down in the back, up in the front, down in the back, up in the front. So you're kind of coming up, you're going like that, right? Up in the front, down in the back. So that north must be over there. Sure enough, that's how they've labeled it. We're kind of checking their work, right? So sure enough, the second hand rule tells us that that should be the North Pole. That should be the South Pole. Okay, so within the magnet, within the coil, sorry, what does that mean for the magnetic field lines? Well, they always go to north, leave north, and then go back to south, right? So they go to north to exit north and then enter south, right? So yes, our thumb points towards north, but really what our thumb is pointing along is the magnetic field line, right? It's just that inside the magnet, north is with the magnetic field lines because they're going to leave north, right, to come back and enter south. Just want to talk for a minute here about strength or flux here, right? Okay. How do we show a strong magnetic field or a stronger magnetic field? What do we change? Well, what did we change for a stronger electric field? We made it more dense, right? We made the field lines more dense. So if you're looking at this, where are the field lines densest? Well, within the coil, right? that kind of makes sense. As they go out, they're allowed to spread out, right? If you look up here, they are less dense. It's actually the same field line if you track it, but as you get further from the magnet, they're going to get more and more spaced out, right? So the field lines are densest within the coil. That's also where the magnetic field is the strongest. Looking at this one, this is just kind of another straightforward example, just looking at how to apply the second hand rule, okay, for current that is in a loop, right? So again, what is that? Current. So which hand rule are we kind of led towards here? We don't have to use it, but we're kind of led towards using our right hand rule. And since it's a circular current, we'll use our second right hand rule, okay? So your fingers become the current. You can kind of see, right? It's tilted a bit on edge, right? It's like this, kind of, sort of. It's not flat like that. It's not really like that either. Sort of like that. So if I follow, right, the current is going that way. And so the magnetic field would kind of be that way, right? But that checks out, okay? So we see these field lines would go around, come back to south. Notice once again, they are the densest in the middle, right? So that is where they are the strongest. So this would be the north face of the magnet. That would be the south face of the magnet. One thing I want to be clear about, okay, because it can be kind of hard to visualize these in 3D when they're flat on paper like this. Notice, okay, I don't want you to think that this side of the magnet is north and this side of the magnet is south. Sorry, of the conductor becomes a north or becomes a south pole. Okay, that is not what's happening here. It is tilted this way, but this side is north, okay? This side is south, the way they've drawn it. Notice the field lines are coming out this way, okay? Going back, entering at south, leaving at north, entering at south, leaving at north, entering at south, okay? So this face, this kind of circular face here is a north pole. This face on the other side is a south pole, okay? So that's what's going on there, okay? The field lines are leaving, circling back, entering at south. Again, right hand rule checks out, okay? What if you wanted to say electron flow? Well, do the opposite, right? Electron flow, if current is going this way, current goes this way, then what would electrons do? They would go this way, right? So try that out. Take your left hand, because it's a negative charge, an electron, take your left hand, and sure enough, still pointing the same way. So that still is north. So this one asks you to kind of explain these in words using your hand rules, okay? So I would suggest just pause it, take a second, see if you can apply your hand rule and explain, especially just what are you basically doing? How are you applying the hand rule? What kind of steps are you following, okay? So pause it, see if you can make an explanation, and then if you want, you can come back and look at mine or just skip ahead to see what I write. So when I look at these, okay, what am I seeing here? Well, I'm seeing that, okay, starting with this one, north is closer to me, right? That's why they've kind of labeled that north. So within the wire, okay, within the circular conductor here, there are dots. What do the dots mean? Well, the dots mean it's coming at you. So within the circle, the magnetic fields are coming at you. What's going on outside of the circle? Well, they're going away from you. Okay, let's think for that about that for a second. But first, let's just apply our hand rule. So we have current. Okay, current is what a positive charge would do. So let's apply our right hand rule for a positive charge. So if current is going like that, then yeah, within the magnetic field, or sorry, within the circular conductor, which is what the thumb points towards, right? Within the circular conductor, this would be north up here, right? North is closer to us. Okay, so that makes sense because within it, the magnetic field should be coming at us. I'm just gonna kind of draw it to help us visualize. What would it look like from the side? Because it can be kind of hard. So this is what it would look like, right? This is how it's drawn. Let's just imagine what would it look like if it were drawn a little more like that, a little on side, so we could kind of picture it. Well, it would actually look like the last one, right? So this is hard to draw. I'm going to try. So this side is closer to us, so it's going to look a bit bigger. Oh, that is bad. Okay. Oh, well. So this is what I've drawn here. Okay. So what would it look like if your eye was over here? If you were looking at it this way. Okay. Well, this is telling us, and we checked with our hand rule, that if you're over here, okay, then if we're looking at, this is what we're looking at, then this should be north, it should be closer to us, this should be south, it should be closer to us, or further away from us, okay? And as we know, field lines, and if we check with our right hand rule, right, within, come towards us, go away, Okay, so within the circle, sure enough, they're coming towards us. Hey, look, dots, they're coming towards us. Outside of the circle, they're going away from us, right? All confirmed by our second hand rule. Okay. Now, what does this mean in 3D? What, because it can be kind of, right, what is going on here? Well, think about it. They're coming at you, they're coming at you, they're coming at you. Do they just go forever? No, they eventually have to loop back, right? Field lines loop back. So on their way out of the coil, they kind of come towards you, but then they eventually must make their way back. And then on their way back, what do? They're going into the page now. So now they're X's, now they're tail feathers, right? And then they loop back through and they come up again here. Okay, so just explaining what we're doing with the right hand rule here. Okay, so essentially fingers are current and then thumb shows magnetic field. Within the circle, right, so as we've drawn here, within circular conductor, okay, B towards us, but then of course has to make its way back, so outside, B away. Right? Just like we've drawn here. So this is two views of the same scenario, right? So right when you're looking at this one, you're you, and then this is kind of a side view of you looking at this one, right? You're seeing that. So towards you in the middle, away from you outside. Okay. What about here? Well, two questions for you. It's a circular motion charge. The charge has a circular motion. Okay. So A, first or second hand rule. And then B, we have current. So should we use our left or right hand version of which of those rules? Well, circular charge, that leads us to second hand rule. Okay, and current is what a positive charge would do. So that is the right hand rule. So second hand rule, right hand version of it. Okay, so current is going like that. Sure enough, that tells me a magnetic field is into the page, right? And sure enough, they've told us that south is closer. So within the coil, my thumb points towards north. Within the magnet, my thumb is pointing towards north. That's why south appears to be up here, because down there is north, right? So let's again just kind of say, okay, let's take that and now do this, just so we can kind of visualize what we're seeing a bit better. So if I take it and kind of tilt it sideways, right, I have, again, not the best. But again, if my eye is over here, okay, what am I seeing? Well, I'm seeing, right, according to this, I'm seeing magnetic field lines go away from me in the middle, right? And then on the outside, they seem to be looping back. And now on the outside, they're dots. They're coming towards me, right? So they're coming towards me on the outside and away from me on the inside of the loop. Just going to draw another one. Away from me on the inside, towards me on the outside. Dots on the outside, X's on the inside. Okay, so what does that mean? What kind of pole do we have here? What's closer to me? Well, remember, they enter south and they leave north. Enter south, leave north. Within, they point towards north. So what's closer? Where are they? Are they entering here or leaving? They are entering. So this must be my South Pole. Hey, sure enough, that's what they said here, right? This must be my North Pole. Okay, that makes sense. So once again, nothing's different here. The fingers are the I, the current. Okay, thumb shows B field, magnetic field. Okay, here though, within circular conductor, okay, B is now into the page. And outside, B is out of the page or towards us. Question for you. If I have this setup, okay, this one, how can I turn it into this setup? Well, you might have said just look at it from the other side. Okay, true, sure. What if I can't do that though? What if I can't get underneath it? Do I have another option? What if I just change the direction of the current? Right? If I just change the direction of the current, well now suddenly my right hand rule would get flipped, right? So if I start here, just flip the current around so it's going that way, and hey, I've just gone from this to this, right? Just like we did with our nail when I showed you on the test magnet there, right? By flipping around the flow of electrons, I flipped around the poles of the electromagnet. So this example is now on page 8, okay, and they were nice enough to tell us the arrows show the direction of electron flow labeled the north and south pole. So arrows show electron flow, not current. Well, okay, looking at this, they told us electron flow. Again, we could use current, but they told us electron flow. Let's just roll with it, okay? Which hand rule? Left or right? Okay, left. It's going to be a left-hand rule. And is it going to be the first or the second hand rule? Well, is the current straight and the magnetic field circular, or is the current circular and the magnetic field straight? Right? Okay, the electron flow slash current are circular, right? It is the magnetic field is going to be straight within the coil anyway. So we aren't to use our second hand rule, okay? So let's use our left hand, our electron hand, okay, or our negative charge hand, and think about how do I move through here? So you can kind of see they go behind. So you can see here, they've given us the up arrows, okay? So the arrows are going up if your electron flow, okay? So that means on the front, if you kind of think about grabbing this, right? Which way is north? Well, thumb points towards north. So this is north. This must be south, okay? Yes, the thumb points to north, but really what that's doing is pointing along the field direction, right? Because within the magnet, the field is towards north, so that it can leave at north, go around to enter at south. Last kind of example for our second hand rule, we have this is a common type of example, okay, where it gives you two sort of setups and says, will these things attract each other or repel each other? So how do we figure that out? Well, we've got some magnet here with a south pole. Okay, so the south pole is there. What would make these attract? What would have to be here on this end? Well, we would have to have a north pole to make them attract, right? How would they repel? You guessed it, if there was a south pole on this end. Okay, can we figure out if this thing has a north pole induced here or a south pole induced here? You betcha, we just got to use our second hand rule, okay? So if I'm an electron, they gave us electron. Notice, okay, what does it do first? First, it goes kind of behind, right? So first it's going in behind, okay? And then it's kind of coming up that way. So it's going in, down, behind, and going that way. So within the magnet, thumb points towards north, right? So that must be north, okay, which makes that south. And so we have south and south. What are these going to do? Attract or repel? Like repel. Like poles repel. Okay, so I kind of had mentioned this term earlier when we were talking about the electromagnet that I showed you with the nail in the middle, right? The one I used in the thing that got hot, okay? A solenoid, that's just a coil of conducting wire, essentially what we've been talking about this whole time, right? For this topic anyway, right? So this is a solenoid, okay? And then when you add a ferromagnetic material to the core, right? So like a steel nail, for example, in ours, the magnetic field becomes stronger, and you call that an electromagnet. Not only does it become stronger, but you can also, through the alignment of domains, you can kind of end up making at least a you can temporarily magnetize it even when there's no current flowing. Okay. However, it becomes stronger because when that current is flowing, you align all of the domains that are in there, right? So if they look like this at first, once you get that current flowing, what's going to happen, right? You're going to induce a magnetic field, perhaps like this, okay? Just making this up, perhaps like this, okay? And then what's going to end up happening? Well, those little domains are going to get aligned along the magnetic field. By the way, I just kind of made this up randomly. This is wrong, right? As we just saw in our example, we saw that it would go the other way. Okay, so don't put too much stock in this. I'm just trying to quickly draw out what's going to happen to those domains in the ferromagnetic core. They're going to align along the magnetic field, right? And so now you've got this thing kind of making its magnetic field, amplifying the effect of the solenoid, which is inducing a magnetic field with that circular current. Last example for this topic, just a kind of reminder of where we've been, where we're going, right? Never hurts to just take a breath and say, what do we know about, how many fields do we know, and how are they different? Okay, so this asks us to distinguish below which one's a magnetic field, which one's an electric field, and which one's a gravitational field. Let's start with number 1, okay? Looking at number 1 here, is this a magnetic, electric, or gravitational field? Okay, magnetic. Could this be a magnetic field? We have some positive charge here, right? Is this what a magnetic field does? Does it go radially inward towards a charge? No. So 1 is not a magnetic field. Could it be an electric field? How do we find the direction of electric field? We define it as in the direction of the force a positive charge would feel, a positive test charge would feel. Are you telling me a positive charge, if I put a positive charge there, it would feel a pull towards this guy? No, it would feel the opposite, right? It would be pushed away, like repel. So that cannot be a electric field. That only leaves gravitational field, but does that check out with what we know, right? Yes, okay, if this has mass, then its gravitational field will be radially inward, right? Much like Earth's gravitational field, or anything's gravitational field for that matter. So gravitational field must be 1, okay? 2, this looks more to me like an electric field, right? As we said, if I'm a positive test charge, what am I going to feel? I'm going to feel repulsion, right? Repulsion away from that positive source charge. Okay, so 2 is definitely an electric field, which, yes, by process of elimination makes this the magnetic field, but let's also think about it. And also, I have a bonus question for you. Which way is this positive charge moving? Is it going into the plane of the page, or is it going out of the plane of the page? So dot or X, essentially. Try out your right hand rule. Okay, try out your right hand rule. If this is the magnetic field, right? If this is the magnetic field, which way is that charge moving? Okay, so take your right hand, put your thumb out of the page. Does that match up? No, if you're doing it right now, following along, your fingers would be curling this way if your thumb's out of the page. Put your thumb into the page, your right thumb into the page. Aha, there we go. Notice how now it does it the right way. So this thing must be moving not out of the page, but into the page. Okay, it's an X, positive charge moving into the page. Magnetic field, definitely 3. Okay, you can now do all of assignment 12.1. That wraps up that topic.